Review of my submission for Program 1 Search Methods assignment. For this assignment, I decided to do a website, and it's built in TypeScript, which is typed JavaScript essentially, with React as a front-end framework and Next.js as a framework for deploying the website. If you want to navigate to the site, you can go to search-methods-assignment.vercel.app for yourself, but we'll be going over it to you. Popping over to the Search Methods tab, we'll see immediately that both of the adjacencies and coordinates files are hosted and parsed at runtime as per assignment instructions. These are hosted by the web server, and so when I hit populate, both of these will be parsed and the graph data will be sent back to the client. So the graph is populated here. The edge weights are calculated using the hover-seen distance here, which will just give us a point-to-point distance across the globe. Starting off with our brute force algorithms, we'll go ahead and start and take a start town and end town, search for Topeka and Bluff City, which should give us good distance to work with. We'll start off with breadth first. So the code for this is in actions right here, and a couple of choices have been made in terms of implementation. Firstly, we're going to break when we find the end town, just to try and keep that shortest path, or keep that path as short as possible. Secondly, instead of merely storing which nodes we visit, we're going to store the edges themselves just to give a visually sort of sense of the order in which it traversed, except for, we'll also see the traversal order explicitly stated. And lastly, we're going to keep a list of the visited nodes, which is necessary for running breadth first on an undirected graph. So we'll go ahead and run that here, and we'll see we get our answer in 0.29 milliseconds with the total distance of 2,500 kilometers. We have a similar implementation for depth first search, except for that we're using a stack instead of a queue. And so we can see that here. We get a slightly better path length of 1,200 kilometers. Moving on to IDDFS, we have a pretty standard implementation aside from those exemptions I mentioned earlier. And we iteratively call DLS path with progressively higher max depth levels. You can see that here. And we do find our end town. Moving on to our heuristics, these both pass through a common search heuristic function, and the only difference between our best first and A star is going to be that cost function. So our search heuristic function will order these in priority queue, which are sorted at each iteration, and the lowest cost one is then popped and selected as the next town. For best first search, our cost function is merely the distance between that potential next town and the goal. And we'll see our performance here. So if we were at Pratt, we're comparing whether we want to go to Cheney and Zenda. Zenda has a lower hover-seen distance to Bluff, so it's selected, but it turns out to be a dead end, so we go back to Pratt and over to Cheney, and so on and so forth. Moving on to A star, this is going to sum the cost of traversing to Zenda in that instance, as well as Zenda's distance to Bluff. So it's taking in basically the total distance. And we see we get the best performance out of any of these, which will result in 500 kilometers. Now this still isn't necessarily the shortest path, since A star is a heuristic in and of itself, but it should give us a fairly computationally efficient answer to our question. And as I mentioned earlier, you can try and check out this website for yourself. It's just at this URL right here. And all of the code is hosted at spaghetti/search-methods-assignment on GitHub. So it's all open source there. Thanks for watching.